on the derivative and Codacci equations for 3D sub-Riemannian structures.
Yes, thanks. First of all, of course, I want to thank organizers for giving me an opportunity to give a talk here. Last time I was a little bit ill, so I couldn't give a talk.
Last year?
Yes, last year. I want to present some calculations that I did not very long ago, and it concerning some thoughts about covariant derivative or connection for some sub-Riemannian structures, and I'm almost sure that all of these calculations was done before somewhere, and I will be very grateful to hear some comments or references about this, because my knowledge about this is poor, I think. So let me start with some classical things about geometry of the surfaces. So what is the surface? Surface is a map that depends on two parameters, u1 and u2, that goes to R3. We can consider R1, this is dr or du1, R2, this is dr or du2. This is the two tangent vectors at any point that forms a basis of tangent plane, and you can uniquely construct a normal vector field by this one, and you have a basis of your space. It is changed, and it depends on the point of your surface. So everybody knows that this is surface sigma, and using these vectors and the product, standard Euclidean product that we have here, you can write down the first quadratic form. This will be this. This is the scalar product in this tangent plane, and you can define the second quadratic form. And these two quadratic forms define the geometry of your surface entirely. So, and what is the main geometric characteristic of your surface? This is a Gaussian curvature. Its definition is this one, and well, everybody knows that. And there is a, well, I'll tell it a little bit later. So, okay, and we have this basis, and we want to understand how does this basis change when you change this point on your surface. This is very well-known equations. And from, well, it's, this is the second derivative of R. You just calculate the second derivative of this vector, and this will be a three-dimensional vector too, so it can be considered as a linear combination of these three vectors. It is obvious. This is a definition of Christoffel symbols, and it turns out to be that the coefficient that stands here is the second quadratic form. It is easy to check this. And there is this equation is called derivative equation for a surface. And and also you can calculate that so we write down how does these two vectors change, and the normal change by the following formula, this formula called Weingarten formula. So, and from you can unit these two equations and consider this one. So you just, I want to put all the things about surface on this small blackboard, but I think this is impossible. Okay, so you just write down this. So this is a two matrix equations, where, for example, A1, you can see what is its component from these two equations. Gamma 1, 1, 1, gamma 1, 1, 2, B1, 1, gamma 1, 2, 1, gamma 1, 2, 2, B1, 2, minus G1 minus B1 G2 0. And this is the first one matrix, and the second one is analysis. Well, so what's then? Then you can consider this thing. The derivative there commute. And if you will substitute these equations, then you will get matrix equations on matrices A1 and A2. This equation called Codacci equation, and it looks like as follows. So this matrix that write down on the left hand side is identically 0 if you have any surface. So you just compute all things, and at the end you will get a 0 matrix, which is not very interesting, but still. What else can we extract from this equation? Actually, if you write down components of this matrix, these components obviously will depend on these quantities, and for example from this quality you can extract the Gaussian main theorem of the surfaces. It states that Gaussian curvature actually would be defined only as a function of the first quadratic form. So this equation lives here. If you will just consider components of this matrix. And also, this is Codacci. Equation. And also there is another theorem. Why how can you see that this thing that is actually is B11, B22 minus B12 squared over G11, G22 minus G12 squared? How can it depends on the coefficient of the first quadratic form? You should know another theorem that that Christoffel symbols also can be calculated using only first quadratic form. So it is all well-known things from the differential geometry. And what can I say more? These symbols, Christoffel symbols, actually they define the connection of your Riemannian manifold. So in high dimension you just define your Christoffel symbols as here, if you have some coordinate from your manifold, and you get your connection. And it, as we see, when you have coordinate system on your manifold, it can be defined using only the metric. So I wanted to repeat all this stuff, not for a surface but for a bracket generating distribution. So what will be the change? We don't have any surface, because if you have the distribution that is non-holonomic, it is non-integrable, and you don't have any surface. You just have two vectors at any point. So this will be turned to x, this will turn to y, and the Lie bracket will be z, or maybe there will be 2 for some reason, for some small reasons, and this z will be n. It's very, I think, natural generalization, because you see this is the tangent vector to your surface, and this is a tangent vector to your surface, and this x and y, they are admissible directions, so you can move only in the admissible directions. It's just the same in Riemannian case to move along your surface. So and I want to repeat all this stuff just for when I have basis x, y and z. I'm sure that it has been done maybe in different terms somewhere, and I've done this calculation for some concrete examples. Okay. Even I can note that, for example, here in this setting, z is a Lie bracket of these two vector fields, and it is skew symmetric. Yes, Lie bracket depends on x and y, it's skew symmetric. And when you multiply n as a vector product of R1 and R2, vector product is skew symmetric too. So it's, I think it's almost the same actually. Just you draw some, but you don't have a surface, but the formulas stay almost the same. There will be some differences, and I want to show them. Okay, for Heisenberg group, it is very easy. X is dx minus dz. Y is dy plus x dz. Then you, well, z is just 0, 0, 1, and this is a bracket. Next, you should find the second derivative of it. Then, well, it is easy to see that this is 0. I will. So this is derivative of vector field x along itself. So not v derivative, but the standard derivative. You should, if you want to compute the thing, you should just write down here. So delta x is delta x, and here I put down the components of this vector itself, minus y. And this is 0. Okay, yes. Or also this will be for this one, and yes, I didn't say the very important thing, actually, that all this matrix, this is a skew-symmetric matrix generally, and it can be identified with some curvature. If you will identify these derivatives, special derivatives, that is there will be two derivative, and this will be the commutator of this two derivatives. This language, I think there are a lot of computations of this in the gauge theory in physics, which are concerned with the theory of calibrated transforms, but I don't know well this stuff. And next, this will be d by x, and this will be it is easy to see, yes, just because z should be dy x minus dy x, yes. So you can just write down these two matrices. The first one will be A1, almost all zeros, and A2 will be 0, 0, minus 1 half, 0. And this quantity R, if you will put it down, it will be 0. So, of course, this example is not very interesting because almost everything is 0. And I computed this thing for the case of SU2. And of course, as I should generalize the Codacci equation from the theory of the surface, I should consider some coordinates on S3. So just S3 is quaternions such that its length equals to 1. Everybody knows what quaternions are. And for example, this q is equals to x, y, zt. This is just x plus y. Then you consider three vector fields iq, jq, and kq. They all will be orthogonal to q, and this they will just form the tangent space to the S3, and well, it is easy to see just like you have a two-dimensional sphere. The tangent plane will be all vectors that orthogonal to this point from 0 to this point on your sphere. Here is just the same, and you can put down coordinates, and I choose this one. So q will be consider three vector fields d over d theta of q, d over d phi q, d over d psi q. This will be three vectors that also form the basis of the tangent plane, but these vectors are not orthogonal in the standard sense of product in H. Then you replace your basis, your frame, and consider this frame. Z is IQ, and this is the same as d over dx. X is KQ, Y is JQ. And there is a non-trivial formula that form dependence between these vector fields and this. So these three vector fields will be just orthonormal frame of the tangent plane to the three-dimensional sphere. And it is true that x, y is equal to z. So I have explicit form that depends on this vector fields, and I can check that this is true. And they are very similar to the formulas for the Heisenberg group. I should mention that this two is just because you can renormalize your vector fields, but it won't be global vector fields. It will be only local. Okay, what then? Then you compute everything the same, and you can check, for example, that in this setting Christoffel symbols, for example this one, it will have very non-trivial form. So why I did all this stuff? I wanted to find in some concrete examples, can these symbols, Christoffel symbols, can they be defined using only the scalar product of these two vectors, two admissible? And I think that it is impossible because, well, the big idea is to just to define a covariant derivative or a connection for sub-Riemannian structures. And here I don't see any formula. You see, there was a formula here that shows you how does the Christoffel symbols can be derived only with using the first quadratic form. These two vectors that are divisible, they are orthonormal in the standard sense of here. So the scalar product is just a unitary matrix. So you can, if you will differentiate it in any sense, you won't get these non-trivial components. So actually, in this, so I'm up until now I'm very pessimistic about defining some unique canonical connection for sub-Riemannian structures, because even in this very simple example I don't see any how can it be done. And still, using all these formulas, there will be another 6 components and 6 Christoffel symbols. The components of the second quadratic form. Actually, it won't be symmetric because now this is only the components in the decomposition of the second derivatives through the first one, through the x, y, and z. They won't be symmetric, So it won't be a quadratic form. And the last line will be just 0. 0, 0, 0. And these are all components that are depends on the psi and theta through the trigonometric functions. And also you can calculate this r, put down in Dynamical and calculate it, and it will be the following one. 4 minus 4. So in some sense this is a curvature and it is constant. Of course this formula is not very surprising because actually it is a sectional curvature of the two-dimensional sphere that in the Hopf vibration. But if you remember that this was the Hopf vibration and blah blah blah, if you consider only the sub-Riemannian structure with these components and you just multiply and in the end you get this constant curvature, and I think it's nice. So just some remark that when I've calculated in Maple, I put down it some instead of sine I put somewhere cosine, and this matrix was huge, absolutely huge. When I find a mistake, it just blows down here, and it was very nice surprise for me. So this illustrates that the Heisenberg is flat, some flat sub-Riemannian structure, and the structure on SU2 it can be associated with some constant curvature structure. All this stuff can be repeated also if you are in the Cartan, if you want to use Cartan method. So I just put down this one. This is do not involve any coordinates, and in this setting all the Christoffel symbols will be 0, but still the resulting this matrix will be the same. This, and you repeat all of them. The A1 will be 0, 0, 0, 0, 0, 2 minus rho 0. So in this setting, in Cartan method, you, instead of consider the standard derivative from one vector field along another, you consider the lead derivative, which is actually this uv, this is just a Lie bracket. So this calculation is much faster, and at the end it will give the same thing. And R will be 0 minus rho to rho u. So, and well, this calculation, I don't know, probably it was done somewhere else, but maybe not from this point of view. And actually what I wanted to find, as I said, some formulas, some ideas how I can define a connection on the sub-Riemannian structure. And I didn't manage to do this, but I have 15 minutes left. What was it for? Actually, my initial idea was to define a holonomy group, or probably holonomy algebra for sub-Riemannian structures. What is this? I will describe it very briefly and roughly. So if you have a Riemannian manifold, you consider, you fix some point, you consider all the loops with beginning and end, which begins and end in this point, and you consider a vector, some tangent vector v. You consider a parallel transport, and the parallel transport, it is of course generated by connection, because, well, okay, it generated by connection. Vector was v, you transport it along the loop and you get this phi of v. Then this phi will be element of the group SON. If you consider all the loops, you will get the subgroup of this. This subgroup called holonomy group. So you see that this thing depends highly on the parallel transport on your manifold. And what is known about this group? There is a theorem of Berger that states that holonomy group can be the following one: UN, SUN, SPN, SPN dot SE1, G2, and spine 7. I don't want to talk a lot about it, but what you can see that in this case, in this one, in this, and in this, your manifold is Ricci flat. So one might say that the more that if your holonomy is small enough, then you have some restrictions on the curvature of your manifold. So the smaller holonomy, the more flat your space. It's very rough.
Bigger holonomy.
No, smaller. Because
bigger group.
The holonomy of the flat space is just unit.
Actually, yes, there is more flat. Yes, that's
yes. So it's very rough instrument to understand how flat your space is, and it can be actually to solve this equation is very hard. It's second order equation, and if you want to find some special holonomy, you usually solve first order equation. So I would like to invent some very rough instrument to understand how flat your sub-Riemannian structure is. And you see, for example, what is the technique of Professor Agrachov as a thing? They consider with his students, Italian guys, consider the geodesics in sub-Riemannian manifold, and they know the variation of these geodesics. From this and the second variation formula or the Jacobi equation, they can extract the curvature of the manifold. They cannot define exactly the curvature, but from the behavior of the geodesics, they can extract some kind of curvature. So it's it is a way to understand how curvature should look like. So in this thing there is a theorem of Ambrose and Zinger that states that the holonomy algebra, this is the subgroup and this is the algebra of this subgroup, it is generated by the following things. So you have a Riemannian tensor. Actually it's not true, this is a lie, but I don't want to specify. You should put here some Okay, this is a skew symmetric matrix because of Bianchi identity and so on. So you consider all the vector space, and this is for all vector fields. For all vector fields, this will be the set of some skew symmetric matrices, and the span. I will put this pattern like a span. The span of all these matrices will be the Lie group, Lie algebra, and this algebra will be exactly the Lie algebra of the holonomy group. So I imagine that, for example, for Lie groups, the following formula is true. The following formula is true, and if you put this formula to the standard formula of the Ricci tensor, you will get the following, that Rxy u is equal to 3/4 xu x. This is true for Lie groups. Imagine that we have not a Lie but Carnot. And consider that the thing is just, by definition, is the following one. And consider consider the span of all this stuff. And again, I just at the end I want to present some definition of holonomy algebra. Actually, I called it holonomy filtration, which is, I think, natural. So this is my definition of this thing, and then for general case we have bracket generating distribution. This is V0, V1 is V0, V0 plus V0, and it is spent on the x1 and x1. So again we have V0 lies in V2, and well, everybody knows it already. And my definition of holonomy filtration of Lie, I don't decide how should it be called yet, is the following one. So this is a subspace in the Lie algebra of SON, where n is the dimensional of the distribution, the height dimension where it lies. And zero holonomy is just generated by vectors you input from here. And the L well, so instead of Riemannian case, when you have only one holonomy algebra and its Lie group, Lie group is a holonomy group of your manifold. Here we have some this thing, some filtration of the subspaces of the, here we have holonomy of SOM. This is equals to, it's just skew-symmetric matrices. And you should understand that if you have non-trivial distribution, this won't be a sub-algebra of this one because it's not non-integrable. And if your distribution is integrable, it means that these vector fields are tangent to some sub-manifold of your manifold. Then this theory will be vanished from this point. The holonomy group will be just the holonomy of this submanifold, and it will be just the same as in the Riemannian case. And more than this, if you will calculate all this stuff just for Heisenberg and for SUN, you will understand that for Heisenberg all this series is zero, so it might say that the Heisenberg sub-Riemannian structure is flat. And for SUN it stops on the second side. Maybe the more complicate your sub-Riemannian structure, this involving will be more long. Yes, and if there are a lot of zeros here, then more your sub-Riemannian structure is flat. So this kind of apparatus, I want to, for example, to check how does this series looks, for example, for Gaussian distribution and maybe something else. But still, I think that this construction is natural. For example, I know that there is a paper where some guys define some covariant derivative and they calculate the holonomy group of the Heisenberg sub-Riemannian space and they get the SOM. So it will be the highest. Although I think the Heisenberg space is the most flat among sub-Riemannian. So I think my construction is much more natural. So yes.
Are there complications?
But you check, but in fact it is not clear if it is indeed intrinsic, so it depends. As soon as you have
No.
vector fields,
No,
you
it's not.
construct things, but if you rotate
No, I don't think that it is intrinsic. It depends on
the
this
frame,
vector.
so you have characterize a frame which give a, maybe
Yes,
the
yes.
idea is to find a frame which give a smallest possible holonomy. Then it
Yes,
will give a
actually,
measure of curvature.
This should be checked. I didn't do this.
Yes, to characterize those with smallest holonomy, then it would be natural definition with smaller holonomy. Because indeed for
Yes,
for
actually.
parallel transport here there would be not I totally agree with you, there are no natural linear connection which produce it. But it doesn't matter that there are no natural parallel transport, most flat way. Simply the connection simply not linear, and that's all. When you change the curve, you change.
But yes, but my
A
idea
kind of
was
connection there is, but it's just more general.
maybe.
There is one connection.
I just want to produce some instrument that could say how flat is.
Yes, it
It's
could be not a
very
bad
rough.
idea. Try to characterize frame which give you smallest possible holonomy.
Yes, yes.
Then it would be measure of how curved your
I
space
see.
is.
But yeah. Yes, actually, I should find some example. Yes, I should prove that if I choose another basis, then
It will
this
be
it can be changed or no. I will just I didn't do that. I should check.